Bonjour. Bonjour tout le monde. Hello everyone. Can you hear me? Yep. Okay, perfect. Bonjour à tous et bienvenue à la Royal Society. Je m'appelle Martin Dionne, je suis directeur des affaires politiques et publiques à la délégation générale du Québec à Londres. Don't worry, it's not all in French tonight. Just a few opening remarks. So my name is Martin Dionne. I'm the Director of Political and Public Affairs at the Quebec Government Office in London. I'm here on behalf of our Agent General, Madame Geneviève Brisson, who needed to be in Quebec this week and sent her regrets and best wishes. Before we start, quick housekeeping. I would like to mention that there is no fire alarm planned for this evening. Should an alarm go off, we all need to evacuate the building. Please follow the employees, and the door is right there. It's a great honor to welcome you to the Quebec Annual Lecture, co-organized this year by Université de Montréal. The Quebec Government Office in London represents the interests of Quebec in the United Kingdom, Ireland, and the Nordic countries. Our mission could be summarized as bringing Quebec's talent, expertise, and vision in the world to our territory. This objective behind the Quebec Annual Lecture is to showcase outstanding Québécois and Québécoises whose achievements have made significant international contribution to their respective fields. Over the years, artists, business people, climate change experts, even astronauts have graced the stage in London for this special occasion to share their wisdom, their talent, and make Quebec shine brighter. Therefore, we are absolutely delighted to welcome this year Professor Gilles Brassard, who embodies the spirit of the Quebec Annual Lecture. A world leader in his field of research, he is one of the pioneers of quantum cryptography. In 1984, alongside Charles Bennett, he proposed the first fully functional quantum key distribution protocol known as BB84, widely regarded as the foundation of modern quantum cryptography. Expert in a topic that few truly understand, including me, Professor Brassard is also fully aware of the astonishing powers and the potential dangers of quantum technologies. Where could those emerging technologies take us, and what can we do about it? This evening presents a rare opportunity to hear Professor Brassard thought on those questions and the reflection of a panel of experts, Sir Peter Knight, Professor Sandu Popescu, and Professor John Rarity, led by a discussion by Michael Brooks. 2025 marks the United Nations International Year of Quantum Science and Technology and represents a unique opportunity to highlight the diversity of contribution to the field. I learned recently that at its beginning, quantum mechanics was known as, pardon my German, Knabenphysics, which means boys' physics in German. The field has evolved far beyond those early days, and women now play a leading role in quantum research. While they may not be on the stage this evening, we want to acknowledge their expertise and genius that propel major advances in quantum science around the world. Quebec Annual Lectures create a unique connection between Quebec and London, a moment of discovery, of learning, of inspiration. This is what I hope this evening with Professor Gilles Brassard will bring you, a privileged encounter with a unique mind. I wish you all a wonderful evening, and I'm pleased to invite Monsieur le Recteur Daniel Jutras of Université de Montréal to say a few words to you. Merci à tous et bonne soirée.
Fellows of the Royal Society, distinguished guests, it is truly a great honor for me to be speaking here at the illustrious Royal Society, a foundational institution of modern science and the guardian of an intellectual tradition that has inspired researchers around the world for 365 years. The culture of inquiry that is nurtured by the Royal Society, embodied by its motto, Nullius in Verba, has shaped every university, including my own. It's a privilege for Université de Montréal to count one of its most eminent professors, Gilles Brassard, among the foreign members of the Royal Society.
Fellow.
Yeah. I'm sorry, you're right.
Commonwealth are allowed to be fellows. Yes.
Alors que nous soulignons cette année le centenaire de la théorie quantique, j'ai le plaisir de vous présenter ce soir un scientifique qui a su en repousser les frontières et en révéler toute la portée. As we celebrate the centenary of quantum theory, I'm delighted to introduce a scientist who has pushed back its boundaries and revealed its full scope. In the 1980s, when quantum computing was in its infancy, Gilles Brassard had the intuition that the laws of quantum mechanics could be applied to make communications completely secure. Together with Charles Bennett, he pioneered quantum cryptography. And today, at the dawn of the quantum computing era, it has become the cornerstone of data protection on the internet. Gilles Brassard has received many prestigious international awards, including the Breakthrough Prize in Fundamental Physics, the Wolf Prize in Physics, and the BBVA Foundation Frontiers of Knowledge Award. In Canada, he's received the Killam Prize in Natural Sciences and the Gerhard Herzberg Canada Gold Medal for Science and Engineering, the country's highest scientific honors. These distinctions are well-deserved, for Gilles Brassard is a veritable titan in his field, one who has been sharing this knowledge with his students and the international scientific community since he began teaching at Université de Montréal in 1979. He came to Université de Montréal, I was told, it's hard to believe, at age 13. Is that right? Am I getting this right?
Correct.
Not as a visitor, as a student at age 13. And I think it's fair to say that he spent his entire life with us at Université de Montréal. So we're very proud to bring him to you tonight at the Royal Society. I would like to thank Sir Peter Knight, Sandu Popescu, and John Rarity for joining us today. The discussion among these great minds promises to be both stimulating and enlightening. And we're also very fortunate to have Michael Brooks as a moderator. We could hardly have found someone better qualified for the job. Not only is Michael a renowned science journalist and prolific author, but he also holds a PhD in quantum physics. Special thanks, in closing, to the Quebec Government Office in London for organizing this event. The entire team was wonderful. And in particular, I would like to mention Lynn Rivard, the outgoing Agent General, who was instrumental in making this collaboration and this event possible. Thank you, everyone. I wish you all an excellent evening in the company of Professor Gilles Brassard and his guests.
Bonsoir à tous. I'm kidding. There are a few reasons why I'm here, but my French is not one of them. Thank you for coming out tonight. It's a great honor for me to be able to introduce Gilles Brassard to you. I just wanted to let you know before his talk the format that this will take. So Professor Brassard will talk for about 45 minutes. After that, we will have a panel discussion. I'll invite the three eminent FRSs onto the stage to have a conversation. But I want to encourage you to think of questions for yourselves as well for the panel, because after we've talked for a certain amount of time, I'll be inviting questions from the audience. And we'll have also questions from those who are watching online. So have your thinking caps on. I've been actually only given 1 minute in the time schedule for this introduction, so I'll keep it very brief. I think Professor Brassard's biography on the Royal Society website provides a particularly wonderful summary. It says, his work has elevated quantum information science from what seemed to be a fringe pursuit to an internationally thriving research field. And his talk, which will no doubt unpack the reasons for that elevation, is entitled A Celebration of Quantum Theory. So let's welcome him to the stage.
All right. Working? All right, good. Well, thanks. Thank you all for coming. Could you please display my screen? Whoever is good. So thank you all for coming. Today, actually this year, we celebrate the centenary of quantum theory, sort of. And for that reason, the United Nations have proclaimed 2025 to be the International Year of Quantum Science and Technology. Again, because it recognizes 100 years since the initial development of quantum mechanics, and specifically something that happened on the island of Helgoland in Germany in June of 1925. And for that reason, there was a major conference that took place in Helgoland in June of this year to overlap with the time when Heisenberg was there, and when he really made quantum theory formal in a sense. It was there already, but Heisenberg was the first to codify the mathematics behind it. So this conference was really very nice. As you can see here, there were lots of people on the island. And these were the speakers and panelists, in addition to very many attendees. It was really a major thing. And this is a stone that commemorates when Heisenberg, one night, by the way, he was there because he was suffering from hay fever. And Helgoland is a remote island with pure air. So he went there to put his hay fever under control. And he spent a couple of months, I'm not sure exactly how much time there. And one night, he figured it out. And he was so happy that he went up the mountain, because Helgoland, there's a base, an Uterland and the Oberland, with a cliff between them. So this night, he was so elated that he'd figured it out, that he went up the mountain. And that spot, specifically in that spot, now there is in June of year 1925, here in Helgoland, he was the 23-year-old Werner Heisenberg, blah, blah, blah. That's the extent of my understanding German, anyways. And just to tell you, it's really amazing. I was invited to this conference. Again, it took place in June of 2025. I was invited 3 years before. So it just shows the extent to which these people were devoted to this conference. They wanted to make sure everybody would be there, and they sent out the invitation 3 years ahead of time. Well, that happens to musicians and concert pianists but more rarely to scientists. So it was very nice. So, and here in the UK, you're also celebrating. So in November, very soon, there will be the United Kingdom Quantum Week. And I'll be back home, so I will miss it, but don't. I'm sure there will be lots of really great stuff during that week in the UK. But, so the whole world is celebrating quantum, and so are we tonight. And also because it's, well, I don't know if it's because this year is the centenary of quantum theory, but somehow I feel that the Nobel Committee had no choice but to give their physics prize to quantum theory this year. Unfortunately, not to me, but, well, next time. But still, the Nobel Prize this year was given to these three scientists for some work they did, I think, in 1983. So it's old work, old experimental work that they did, which set the stage to quantum technology, and specifically for quantum cryptography and quantum computers, which will be the main topic of my lecture today. So it's very apt that the Nobel Prize was given for those, for this type of research. And it's even more remarkable because only 3 years ago, there was a quantum Nobel Prize already. And only 3 years between two, in physics there are many, many areas. And it's fairly rare that you have the same sub-area of physics that gets the Nobel Prize in such a short interval. So in 2022, was really a time for those three fellows, about which I will talk again later, to get the prize. And then 3 years later, because it's the centenary, they had no choice, they gave it again to quantum theory. But these three fellows got it for pioneering quantum information science. So again, what I'm going to talk about. And I'd just like to point out Anton Zeilinger's very nice quote here. It's probably, it being, of course, quantum theory, it's probably one of the most beautiful theories ever invented. Well, I don't disagree, but I would remove probably. I would remove one of. It's just the most beautiful. It's just the most beautiful theory ever invented. Although I guess the evolution is not so bad either. I mean, the theory of evolution. You know, when I signed the charter book of the Royal Society, it was a very emotional moment for me because I knew that I was signing on top of Isaac Newton's signature, but also Charles Darwin and many others. All right, so there have been two so-called quantum revolutions in history. The first one, what we know as the first revolution, is what we're celebrating this year as centenary, Heisenberg, right? So that's the first quantum revolution, started there, although one could say it started with Einstein. In 1905, Einstein wrote a famous paper that gave him the Nobel Prize about quantum theory. In case you don't know, Einstein did not get the Nobel Prize for relativity. He got it for quantum theory for a paper he wrote in 1905 about or maybe we could just say it started in 1900 with Planck. But 25 again is when Heisenberg got his breakthrough. And it doesn't really matter for us because I'm not going to talk about the first revolution. We're concerned about the second revolution. And the second revolution started with Stephen Wiesner with a paper he wrote in 1968. And I'll tell you more about it in a moment. So, but before I leave the first revolution, let's just mention that it's at the core of most technological innovations that changed our lives in the 20th century. Like the transistor that gave rise to the computer, but so many other things. Almost all major technological innovations in the 20th century are based on quantum theory, somewhat or other. So the first revolution really changed our lives. And the second revolution that I'm talking about will be at the core of the 21st century. And it hinges on something called quantum information. Now, quantum information it gives us applications, including, as I said, quantum computing, quantum cryptography. Again, if we come back to Nobel Prize this year, the second revolution is what these guys developed from a experimental point of view, and that I developed from a theoretical point of view. And both quantum computing and quantum cryptography play a major role in our yearning for privacy, as I will explain. Wiesner. So who's this guy? Wiesner, in 1968, wrote this paper I will tell you about. And he looked like this at the time, playing Go. He passed away 3 years ago, looking like that. So in 1968, he wrote a paper called Good Coding, which I see as the birth of the second quantum revolution. It's a very, very important paper. And that's the first page, in which he explains that the uncertainty principle, and as you probably know, the uncertainty principle is due to Heisenberg. So we're back to 1925 again, right? Heisenberg is there. Well, not really, but so the uncertainty principle, quoting again Wiesner, gives rise to novel forms of coding. So what Wiesner did in 1968, he was the first person ever, as far as I can tell, to realize that quantum theory could be harnessed to achieve tasks that are impossible in the classical world, as opposed to being able to do some things more efficiently, like an electronic computer. We would not have electronic computers without the first quantum revolution, but everything an electronic computer can do could be done with a mechanical machine, which would be much bigger and take much more time. But there's no impossibility in not needing quantum theory to do what classical computers can do. Wiesner, on the other hand, realized that quantum theory made it possible to do things that are totally impossible, not just infeasible, but impossible in the classical world. In particular, he introduced this quantum banknote. Totally impractical, but it's a beautiful theory. It's a beautiful idea. It's especially beautiful because it's so simple. And I'm not going to describe the quantum banknote. I want to show you this nice picture. A quantum banknote is something that is impossible to counterfeit, but impossible in principle, because it contains quantum information, and quantum information cannot be copied. It's as simple as that. But a banknote, a classical banknote like you have in your wallet, there's no laws of physics that forbids making a perfect copy of it, whereas the quantum banknote cannot be copied. It's not useful, at least in those days. 1968, it's not something that we could actually do. But as a theory, as an idea, it offers an idea that is totally revolutionary, something you could not do classically. In fact, so revolutionary that, of course, it was rejected. So Wiesner submitted his paper to the IEEE Transactions on Information Theory, and 1968, nobody could understand it. So neither the referees nor the editor understood. It was rejected. It was rejected, but, and Wiesner decided to just move on to something else, and it could have been the end of the story. But he talked about it to his friend, Charlie Bennett. And one day in 1970, so 2 years later, in 1970, Wiesner visited Bennett and started talking to him about his ideas. And Bennett took out a pad of paper and wrote this page, more than one page, but the first page, where for the first time in history, as far as I can tell, the words quantum information theory were written one after the other. And I think of this page, this physical piece of paper, which still exists, as the most important artifact of the entire field. And Bennett understood how important the idea was. And whereas Wiesner would have left it die, Bennett decided to do something with it. And while he tried for many years to interest other people, to no avail, until he met me. And when he told me about these ideas of Wiesner, because he's a physicist, Bennett, I'm a computer scientist, cryptographer by training, and it was really the meeting of these two fields, the meeting of physics and cryptography, or physics and computer science. That was the spark that made it real. And so we took off from there, Bennett and me. And this paper, this 1970 paper, not paper, but meeting of Bennett and Wiesner, so this took place 10 years before Feynman thought of quantum computers. So quantum computers were not even on the horizon then. It was 15 years before Bennett and I, invented quantum cryptography, 25 years before Peter Shor discovered the most famous algorithm on a quantum computer, about which I will talk again later. So really, it was really, really before its time, which I guess is why it was rejected. But thanks to Bennett, it did not die. So let me tell you a few things about cryptography, so classical cryptography, the field that I was trained in as a PhD back in 1979. So cryptography is an ongoing battle between code makers and code breakers, or between good and evil, or in some cases between evil and good. It depends on the point of view, of course. From my perspective, I'm on the side of code makers, but I reckon that code breakers like Turing, or I should say Marianne before him, so code breakers sometimes play a very important positive role in history. But still, I'm on the side of code makers in general. But anyways, let's put aside who's good and who's bad. There's an intellectual question that really cannot be avoided, which is who's going to win between code makers and code breakers. And for us today, because it's a centenary of quantum physics, for us today, the really most important question is not who's going to win, which is important, but we live in a quantum world. And does it change the story? Is the fact that we live in a quantum world a blessing for code makers or a curse? And that really is the topic of my lecture. Okay. So a few words how cryptography works very intuitively. You have two, in the simplest case, there's a lot more about cryptography. But in the simplest situation, you have two characters, I'm going to call them Alice and Bob, and they want to communicate. So they're talking, and if you have any imagination, you understood that this is this is clear text, and you can read that. and there is this bad guy who's listening, called the eavesdropper. And the eavesdropper is smiling because he understands everything. So that's why Alice and Bob will use cryptography. They're going to take what they want to say, and they're going to use some method to transform it into something that the eavesdropper will not be able to understand, like this, for instance. And the way it's done usually is through what we call a key. Oh, he's not smiling anymore, right. So we use a key. The key is some information that is shared by Alice and Bob and unknown to everybody else. And the way that cryptography in its simplest case works is that if Bob wants to say this to Alice, he will use an enciphering algorithm, a method, with the key. So the key and the clear text message together will give rise to the ciphertext. And Alice, who receives, so this will be sent in the clear, this will be sent to, through a channel to the receiver, Alice in this case. And if an eavesdropper intercepts that, the eavesdropper will not be able to understand because the eavesdropper doesn't have the key, we hope. But Alice has the key, and she can put it through a deciphering algorithm with the same key and get the clear text. So that's essentially how cryptography works in its simplest case. And for this to be secure, we need two things. We need to find a way to encipher and decipher given the message and the key. And we need a way to establish the key between Alice and Bob. So there are two issues: how to obtain a shared key and how to use that key. But these are really two completely different problems that they both must be solved independently. And once you have a solution to these two problems, then you can communicate in privacy. So how to obtain a shared key is called the key establishment problem, and how to use it is going to be enciphering and deciphering. And in this talk, I'm not going to talk about how to use the key, how to encipher and decipher, except to say that it's important that the method used to encipher and decipher should be publicly known. You should not put your secret in how you proceed to encipher and decipher. The secret should be strictly come with the key. And so for lack of time, I will concentrate on how to obtain the shared key. But let me just tell you, there are ways that have been known since the 19th century. If you have a key long enough, it's known as a one-time pad. If you have a key long enough, as long as a message actually that you want to communicate, with a key long enough, you can have perfect secrecy. There's a technique, again, known as a one-time pad, that offers provable perfect secrecy, meaning that the eavesdropper who would intercept the ciphertext would have no information about a clear text except for its length. So this has been known since the 19th century. But so the question really will be how to obtain that key. So the key establishment problem. And so how can they establish a secret key? Well, there are essentially three ways. One that is not interesting mathematically speaking, which is a trusted third party. So you could have, no, I mean, but in real life it's been used. During the Cold War, Khrushchev and Kennedy communicated through the so-called red telephone, which was not red, it was not a telephone, but the red telephone was encrypted using a one-time pad by a key that was shared between Khrushchev and Kennedy that was literally delivered by a diplomat. It was stored on a magnetic tape. The diplomat would put a tape in a briefcase, strap the briefcase on his wrist, and take the airplane to deliver on the other side. So in real life, trusted third party has been used very importantly, but it has no interest mathematically. But again, it was used by Khrushchev and Kennedy. So, but we'd be interested in how else can we establish a secret key? And there are essentially two ways. One is known as, one will use computational assumptions. I will tell you more about in a moment. And the other one will use quantum theory. But I'll tell you about those two. But first, let me mention that all methods based on computational assumptions, by definition, cannot be unconditionally secure. Meaning that an eavesdropper with enough computing power can always break that. We can only hope that would take 1 million years of computation. But it's not unconditionally secure by definition. So computational security is an idea that was introduced in the literature by Diffie and Hellman in 1976 in a paper, a very important paper, New Direction in Cryptography, by the way, in the same journal in which Wisner submitted and was rejected in 1968. So New Direction in Cryptography really introduced the notion of public cryptography and of computational security to establish a secret key. And shortly afterwards, an implementation was proposed by Rivest, Chemie, and Edelman, known as RSA. RSA is the most used system today to send confidential information. Slightly afterwards, Michaelis proposed another way to do that. But in fact, before Diffie and Hellman, Ralph Merkle had similar ideas, but whereas Diffie had a professor, namely Hellman, at Stanford, who understood the importance of the idea, and they published, and they were very successful. Merkle had a professor who did not understand, and it took him 4 years, if not more, to get the paper out. So Merkle had the idea before Hellman. He wasn't. Diffie Hellman were at Stanford, and Merkle was Berkeley, next door. But Diffie Hellman were understood faster than Hellman, but nevertheless, we all agree that Merkle was there before. And in fact, before that, there was Cliff Cox in the British Secret Services. And Cliff Cox invented RSA, but of course was kept secret. And before Cox, there was James Ellis, also in the British Secret Services, who was the really first person to think that it could be possible to do key establishment. All right, but so Merkel's idea was in fact never used in real life because Diffie and Hellman's and RSA seemed to was more convincingly useful. So nobody, I think, ever used Merkel's idea. In theory, it's really nice, but in practice, not used. But Cox, after all, he was in the Secret Services, so maybe they used it, but we don't know. And Ellis had nice ideas, also in Secret Services. Michaelis was not used either, and that's a disaster, as you will see in a moment. So, in fact, Diffie, Hellman, and RSA, they are literally used by billions of people every day. Every time you establish a secret connection with a server, it goes through either Diffie, Hellman's approach or RSA's approach. Literally billions of people every day use that without knowing it. And they use that in the hope to secure their transactions. And it's only a hope. Because, again, what we care about is it a blessing or a curse for code makers that we live in a quantum world? And it turns out that in 1994, that's a long time ago, in 1994, Peter Shor and Alexei Kedaev also, independently, discovered an algorithm to factor large numbers efficiently. And it turns out that factoring large numbers efficiently is what you need to break RSA. And the same Peter Shor also found a way, in fact, before, a week or two before, to extract discrete logarithm efficiently, sorry for the jargon, but that's what you need to break Diffie-Hellman. So RSA is broken by Shor's algorithm, and Diffie-Hellman is broken also by Shor's algorithm. And even if you know what that means, variation in elliptic curves. The elliptic curve cryptography is also broken by Shor's algorithm, which has been around for more than 30 years. So you might wonder, how come we're still using it? Well, because lots of inertia, and because in 1994, nobody, well, not nobody, but all these people who are in power and using this cryptography did not think that quantum computers would ever become real, because what I didn't tell you is that Shor's algorithm requires a quantum computer. And with any luck, there is not yet one running somewhere hidden in the basement, capable of breaking all the cryptography, but we don't know that. There might be one. But we've known for 30 years that something has to be done, and that much has been. Well, some now, but much too late. Well, quantum computers, we don't, as I said, we don't have a, as far as we know, we don't have a really large-scale quantum computer that would be capable of running Shor's algorithm, but it's coming. It's coming. This is just an example. This is a quantum computer as it's currently being built by IBM. And just to show you how different they can be, this is the one that's being built in China. In China, they're completely different architecture, different technology, but both are quantum computers. Both are doing things that, both have been able already to do things that are probably impossible in the lifetime of the universe for a classical computer, but so far things that are not useful, that are only useful to prove that quantum computers could do stuff. And we're still waiting for the quantum computers to do useful things, but it shouldn't take too long. We're getting there. So anyways, so the result is that RSA is gone, and Cox is RSA after all, it was not used anyways. Diffie-Hellman also is broken by Shor's algorithm. Merkle is broken by Grover's algorithm. So there's another algorithm, quantum algorithm, that breaks Merkle. And that leaves only Michaelis. And if we had used Michaelis from day one instead of Diffie-Hellman and RSA, we would not be in trouble today. Except perhaps that Shor would have thought it's more interesting to break Michaelis than RSA, if that's what had been used. But he tried that. But, so far, nobody has said that they know how to break Michaelis. Oh, well, we put our eggs in the wrong basket back then. You know, ever since the little padlock appeared in your browser, it's either Diffie-Hellman or RSA. It could have been Michaelis, but it's not. It was not. So you may think that if there's a quantum computer today, my data is gone tomorrow. Well, think again. That's a big mistake. The right thing is that if there's a quantum computer tomorrow, my data is gone today. And this is, I'm quoting this nice gentleman, and this is due to an attack known as harvest now and decrypt later. Because one of the main weaknesses of classical cryptography, by which I mean public key, is that an adversary can harvest encrypted information that goes on the internet or somewhere else, and all the encrypted information can be harvested by someone who is yet unable to decrypt it and kept in storage. And whenever that person gets a quantum computer, well, all that can be taken out of storage and decrypted after the fact. So literally, everything that you've entrusted to the internet in your entire life, all of that will become an open book when a quantum computer is available. At least an open book to people who were careful enough to harvest the encrypted information when it was coming out. So it's really bad, really, really bad. But that's how it is. In fact, there is no way to save the past. The past is gone. The past is, this information is in the wrong hands, encrypted perhaps, and there's no way to take it away from them. So don't even dream of trying to save the past. We can only hope to save the future by using different techniques to protect the information. So who will win? Well, it's a blessing or a curse. It looks like it's a curse, right? It looks like quantum theory is a curse to code makers because of Shor's algorithm. I want to stress that quantum computers have a lot of other potential uses. They will not be used only to break cryptography. Well, we were developing all sorts of algorithms on a quantum computer we don't yet have, but we're already thinking about what we would do if we had it. And also the very positive thing like developing new medications and materials and chemistry and all sorts of things that we will do better when we have a quantum computer. So don't think that quantum computers are evil. It's like fire. Fire is evil if you use it to burn someone or but fire is good for many other things. Okay, but yet other systems like Michaelis could resist. We don't know that, but it's possible. So there's hope. There's hope to replace RSA if you had meant by systems that would resist a quantum attack. And that's known as post-quantum cryptography. It's called this is not quantum cryptography that I'm talking about later. It's post-quantum. It's called post-quantum because it's a cryptography that we hope will survive after a quantum computer becomes available, post-quantum. And so can we replace RSA diffie Hellman by other classical schemes? Well, perhaps. Lots of people are working on it. Some standards already are being developed, but there's no hope for proof of security, at least in our current state of ignorance, almost state of knowledge. We don't have any mathematical techniques to prove the security of any scheme of that sort against a quantum computer, nor even against a classical computer. So if you want to trust post-quantum cryptography, fine, it might be secure, but you will never know for sure. So, and unfortunately, these schemes are misleadingly called quantum-safe cryptography and quantum-resistant encryption by people who have no idea what it's saying. Well, they could be quantum-safe, they could be quantum-resistant, they could be, but we don't know how to prove it, and it could also not be. The way RSA was believed to be secure for years until Shor came along. So anytime an algorithm could be discovered to break these so-called quantum-safe or quantum-resistant encryptions, even perhaps against a classical algorithm, that's also possible. We don't know how to prove otherwise. And as I said before, they cannot be unconditionally secure anyways. So what can we do? What can we do to reestablish security? And the answer is to combat fire with fire. And here, when I say fire, I mean quantum. So we combat quantum with quantum, and that's quantum cryptography. So quantum cryptography is an approach that I developed with Charlie Bennett in 1984 to use quantum effects for the protection of privacy. By the way, 10 years before Peter Shor discovered his algorithm. So in a sense, the cure was found before the disease, 10 years before. And quantum cryptography uses a quantum channel. So you need to be able to transmit quantum information between Alice and Bob. And that is a technological challenge to some extent, but something that we know how to do. It's not in the same league as quantum computers. Quantum computers require much more advanced technology than quantum cryptography. And so we don't need a quantum computer to implement quantum cryptography. And I'm going to explain how it works, but just very, very in a nutshell, if Alice sends quantum information to Bob, and these little things represent polarized photons, doesn't matter if you don't know what it is, but these polarized photons are sent from Alice to Bob. And what quantum theory tells us is that these states, these quantum states, cannot be distinguished, and any attempt at distinguishing them will create a disturbance, so that any eavesdropping attempt will create errors, and these errors can be detected by the appropriate protocols. So that if Alice sends this to Bob, but the eavesdropper in the middle tries to read it or something, then unavoidably the eavesdropper will create a disturbance, and Bob will receive something different from what Alice had sent. And that disturbance can be detected. So Alice and Bob will know that there was an eavesdropper, and they will act upon that. And then we use the quantum channel not to send a message, but to establish a secret key. And once the secret key is established, we use a classical one-time pad to send a message. So the quantum signal will only be used to establish a key. And if eavesdropping is detected, then Alice and Bob know that the key is not secure, they will not use it. Otherwise, they will know their key is secure, and then they can use it safely to send a message, so that the message will not be compromised. The worst that can happen is denial of service. Alice might be unable to transmit her message to Bob, but once she's convinced that the key is secure, it is, and the message can be sent in full confidence. All right, so we prevent eavesdropping. So quantum cryptography is unconditionally, provably, there's a proof that it's unconditionally confidential, meaning that it remains secure regardless of the eavesdropper's computing power and technology. Right. So, who will win? Looks like it's a blessing after all, right? But that's theory. That Bennett and I developed this theory in 1984. It took about 10 years before complete proof of security was achieved. Now we have it. But it's proof of security, again, if it's implemented correctly. So we need to implement it. Not us, we're theoreticians, but other people, some of whom are here now, need to implement the idea. In fact, we built the first prototype. We being Bennett and me and 3 students, we built the first prototype for quantum cryptography, over 30 centimeters, and it was mostly of a joke. It was a proof of concept, but mostly a joke because this thing at the time worked on 1,000-volt range to turn photon polarization, and the biggest piece of the whole apparatus is the power supply, and power supply to, as you probably know, power supplies on big voltage make noise, so we could literally hear the photons go through, which is not so bad. What's bad is the zeros and ones did not make the same noise. So this was provably secure against any eavesdropper who is deaf. But the funny thing is that our theory had not been taken seriously by the research community, whereas this sort of this nice apparatus was taken seriously. We even got to publish in Scientific American, and that's one of the reasons why quantum cryptography took off, because then serious people decided to enter the game. Serious people in terms of experimentalists. Again, we were theoreticians, but experimentalists who heard about it decided it was interesting to implement something serious on longer and longer distance. One of the first implementation was done by Richard Hughes and collaborators for a half kilometer distance. Again, our prototype was 30 centimeters in 1992. And Nicolas Gisin also was among the first people to make a long distance, more than 1 kilometer, on fiber. And John Rarity here, with Paul Tapster and Paul Townsend here as well, built also one of the early prototypes, over 10 kilometers, although the 1993 paper was more about demonstrating interference, and it's like the year after that they actually did something about quantum cryptography. But these were the early things. But today there are companies around the world who make their business in quantum cryptographic apparatus, or one of their products. Like Toshiba is not doing only that, but Toshiba is very, very serious about quantum cryptography. By the way, I'm not endorsing any of these, but I just say a few words about these three. Idée quantique, IDQ is Idée quantique in Geneva, led by Nicolas Gisin initially. And now you can go on the internet. You can buy quantum cryptographic apparatus, and you buy 2 boxes, and you link them by 100 kilometers of optical fiber, and it just works by itself. You don't need to be an engineer to use it. So Idée quantique has been running around, has been thriving for decades. It's very successful. Toshiba is also doing great business with quantum cryptography. In fact, if you go to the Toshiba Wikipedia webpage, and the first paragraph talks about quantum cryptography already. So Toshiba is really serious about it. This is mostly Toshiba, in fact, in England, who is doing that. And Quantum CTEC is the giant in China, the biggest one, actually. In China, Quantum CTEC, they've, in a bit less than 10 years ago, they had a backbone of quantum cryptography that linking Shanghai to Beijing over 2,000 kilometers distance. Now they have 10,000 kilometers in China. The yellow lines are trunk lines of quantum cryptography on fiber for 10,000 kilometers, and they claim to have 5 million users already. By the way, 5 million users, 5 million is not so much compared to how many people are in China. and Diffie-Hellman and RSA have billions of users, but still, it's getting there. And they also use not only quantum crypto over fibers on the ground, but also space-based with satellites. So they built, the Chinese sent the very first quantum science satellite was launched by China in 2016, almost 10 years ago. And they use it to link, they made, I think they're, at some point, they created a key between Beijing and South Africa. So it's quite far with their satellites. They have more than one satellite now. And many countries are in the race for space-based quantum cryptography, including Canada. All right. But Europe is also doing great. In Europe, there is something known as EuroQCI. QCI is in quantum communication infrastructure. And EuroQCI is spanning the entire European Union. Every country in the EU is a partner in EuroQCI. There they are. Of course, unfortunately, you will notice that the UK is not there because of Brexit. Not my fault. Switzerland is not there either, even though Switzerland was among the first countries to build large-scale quantum cryptographic apparatus, but they're not in the EU either. But all the true EU countries are part of EuroQCI. And so in the longer term, we want to establish a quantum internet. And this is not a dream. This will happen. All right, so it seems to be a blessing. Why did I say it seems to be? I suppose it is a blessing, because there's a catch. The catch is that quantum cryptography is, as I told you, was mathematically proven to be invulnerable, provided it is actually built as we designed it as theoreticians, which is not really possible. The actual devices could have imperfections. And some people known as the quantum hackers are very, very clever at tapping into the imperfections of the implementation. And this guy, Vadim Makarov, is the best-known quantum hacker. He has this little briefcase that contains all he needs to tap into quantum crypto networks and break it. Not necessarily all of them, but he's so much imagination and all possible ways to tap into imperfections in the apparatus. By the way, of course, they don't break quantum crypto, they break the implementation. Nevertheless, there's one thing that quantum crypto offers that classical crypto doesn't, which is that if you want to break into quantum cryptographic key establishment, you have to do it live while it's taking place. You cannot do, as I said before, this harvest now. This is Norbert writing this. He calls it future-proof. Quantum crypto is future-proof, meaning that it will be as secure forever as it was right after transmission. Right after key establishment, maybe it was broken then and there, but if not, it remains secure forever, as opposed to classical crypto, which has the harvest now, decrypt later threat that I told you about. So that's the real one thing that quantum crypto offers that classical doesn't, is it being future-proof. Okay, but it's not a magic bullet. It's subtle to attacks, as I said, if it's not implemented properly. But okay, the attack must take place at the moment. Also, it does not offer digital signature. I did not mention digital signatures, but digital signature is the greatest invention, in my opinion, of Diffie and Hellman, 1976. It's not for the transmission of classical of information. It's for signatures. And this is not really, so we still need classical crypto to do digital signatures. And so we should deploy a hybrid solution. A hybrid solution is one in which we use both quantum crypto and post-quantum, knowing that they both have weaknesses, but by using them together and making a key, by combining the keys that you obtain with both techniques, then to break it, you will need to break both approaches. So it gives us more security. And again, if the quantum crypto part was not broken right then it's good forever. Whereas the the post-quantum can be broken retroactively. All right, so can we dream yet of an unbreakable implementation? And the answer is yes, in theory. And perhaps in practice. But very quickly, and this uses entanglement. Entanglement is the most fascinating aspect of quantum theory, the most non-classical aspect. And using entanglement, Arthur Eckert FRS, already in 1999, thought of a different way of doing quantum cryptography using entanglement. And what he proposed in those days was not really more secure than BBA4, but it opened the door to other versions of quantum cryptography that really need entanglement, and with which we know in theory again how to design quantum cryptographic apparatus or protocols that would be secure even if the apparatus is imperfect. No matter how imperfect, as long as you have some classical control over it, that becomes provably secure. And so, yes, it is possible that we're going at some point to have a quantum cryptography that is provably secure, even no matter what, well, as long as quantum theory is correct, which, of course, we never know for sure. So entanglement is the key. And I'm not going to have time to tell you about entanglement, but many people believe that entanglement proves that our world is non-local, that nature is non-local. In particular, these guys, the experiments in 2000, they got a Nobel Prize in 2022 for experiments in the case of Clauser that he did 50 years earlier and 40 years earlier for us. And they believe that their experiments, plus Bell's theorem, whatever it is, establish the non-locality of nature. But they're wrong. And maybe with the panel, we're going to have time to discuss that some more. They're wrong in the sense that everything that quantum theory predicts can be explained in a local realistic universe, Bell's theorem notwithstanding. So all of these nobly worked experiments, the purpose was to vindicate quantum theory, to prove that quantum theory, what quantum theory predicts, really occurs in nature, that is real. But all of that can be explained local realistically. And therefore, none of these experiments prove the non-locality of nature. All right, I will stop here since my time is up. And oh, they've cut me out. No, I just...
Sorry to rush you through. Thank you very much, Gilles. I do hate to be that loiterer who accelerates your talk, but we'll have time to get into the non-local stuff. We had a Zoom call in preparation for this meeting today, and we got into the non-local, is it real kind of thing very quickly on the Zoom call. It very quickly got out of control, so I'm going to try to avoid that tonight, but I feel like I'm not going to be able to. I'd very much like to invite the panelists that we have to come up onto the stage, please. We're going to start to react and talk, react to that talk. Let's take a seat. I will. Not quite sure which microphone to use at this point. I would like to introduce the panel to you. Sandu, would you mind if I take that seat?
Oh, please.
Otherwise I'm going to be looking like I'm watching a tennis match.
All right.
Thank you. So the panelists we have tonight, I'll start with Professor Peter Knight, Sir Peter Knight at the end. Is a physicist renowned for his pioneering research into quantum optics, an extremely influential figure within the wider UK physics community and beyond. In fact, I think we have Peter's influence at the UN to thank for the fact that this is the International Year of Quantum. Professor Sandu Popescu, here, nearest to me, is a theoretical physicist whose research centers on conceptual and fundamental problems in quantum mechanics. He's one of the pioneers of quantum information, and his work has been instrumental in putting entanglement and non-locality at the very core of our present-day understanding of quantum theory. Sandu has been awarded several prizes, including the 2016 Dirac Medal of the Institute of Physics and the 2011 John Stuart Bell Prize. Now, I can't remember whether affiliations were discussed at the start, but Peter has multiple affiliations. I should mention those just in case they weren't mentioned. Is Senior Research Investigator in the Physics Department at Imperial College, a Chair of the Quantum Metrology Institute at the National Physical Laboratory, and Senior Fellow in Residence at the Kavli Royal Society International Centre at Chidgley Hall. Sandu is Professor of Physics at the University of Bristol. And John Rarity here is also at the University of Bristol, Professor of Optical Communication. And John has pioneered a range of techniques in quantum optics, including many of the early implementations of quantum key distribution, as we saw in Gilles' talk. For many years, John was, with his collaborators, the sole UK representative in experimental quantum optics. And he was a co-recipient of the 2023 Messius Quantum Prize, recognizing the significance of his contributions to the field. So please welcome our panel here today. I'd like to start by getting your reactions, really. There will have been things, I'm sure, in Gilles' talk that you want to react to. Peter, let me start with you. Are there sort of comments you'd like to make in response to that, particularly with reference to cryptography?
Right. At the very end of Gilles' talk, he talked about the hybrid solution of bringing together post-quantum and QKD together. That's been the approach that we really do take here in the UK. So if you look at the quantum communication research that we're doing in the UK, if you look at the implementation through the networks, if you look at the implementation by the companies, for example, BT and Toshiba, it's this bringing together of post-quantum and QKD has been exactly what we've been recommending all along. I think it really does come to the heart of the issue that for post-quantum, there are no security proofs. The post-quantum algorithms that are being explored at the moment have been insufficiently tested. We know there are no security proofs for these things. Some of them are lattice-based, and I always worry that a lattice suggests periodicity. Periodicity suggests the Fourier transform. Fourier transform suggests Peter Shaw. So I'm kind of jumpy about some of these things. So we've absolutely pushed the idea that one should have this hybrid solution. And certainly the test network that we have running around between the data centers in London, that's run by British Telecom and Toshiba, where the user is HSBC, is actually using exactly this dual side. If you look at some of the network stuff that's being run, for example, by Richard Penty, who's sitting in the audience here, again, looking at ways in which you could bring all these things together, I think is the secret for this. So absolutely in agreement with Gilles on this one.
Thanks, Peter. And John, I mean, is there anything you'd particularly like to react to?
There are a couple of points that I'll be asking maybe more questions about, but the progress in quantum computation seems to be following quite a high-order Moore's-type law, an exponential growth in the number of qubits. I don't know, maybe an order of magnitude number of qubits every few years. And that means that if you begin to believe that, they will get error correction and such like sorted, then that there will be one in the next 10, maybe 15 years. And that then says, well, we then are able to crack these post-quantum and even all of the RSA, but it also sort of poses questions about this data harvesting. There's a lot of data, and there'll be a lot more data, and one bit for every bit. One bit of key for every bit of data is never going to work, so there is going to have to be some compression or some selection. So I had questions maybe in that direction.
Can I'll just follow up on that, if I may. You were implementing sort of quantum cryptography solutions in the early 1990s, yeah, or key distribution solutions. I mean, did you think or do you think that the progress has been faster than you expected or slower than you expected in terms of implementing the technology?
In quantum cryptography, we've had the solution since probably 2000 when ID Quantique commercialized things the first time. The problem's more been the fact that, and it's not just quantum cryptography, but it's all new things. And the existing security infrastructure that banks and people use is very fixed. They trust what they've got. It's not gone wrong yet. Therefore, they don't need to replace it. And anything that's not been tested, and we've already said, even the post-quantum, is not tested. And so the banks won't necessarily, or the big users, they will not necessarily take on sort of things. I mean, we had a classical cryptographer in Bristol, and he said, yes, I introduced a new scheme for credit card sort of verification or whatever, and it took 20, 25 years for that to be taken on board. So we may have a solution, but we have a big problem, which is trust within the sort of existing infrastructure, the existing sort of security services, etc. Right, okay.
Sandu, let me come to you. I think of you as more rarefied. I don't know if that's fair. You work very much in sort of areas of trying to understand the foundations of quantum theory. I wondered whether anything in Gilles' talk sort of set you thinking, or...
Well, Gilles did many things in his life, very many. And for the purpose of this night, he emphasized more the technological part. So what I thought I would let the discussion now go on the technological thing, and then I will deviate it into more interesting things, as far as I can say.
And I imagine that a number of people are here tonight because quantum theory is fundamentally interesting to everyone because of what we hear about it, about what can't be understood, what can be understood. And you'll be glad to know that there's very much a lot of debate between people who working in the field about what it means and how best to sort of think about it. But you would say that all of the sort of contributions have a valid purpose, don't they?
Well, look. Quantum cryptography didn't start on an empty background. There were many people thinking at the foundation of things. And let me take just one sentence that Gilles said. Discussing about Wisner's paper that was rejected. And you said that nobody understood it among the referees. And indeed, nobody understood it. Now, what you should appreciate, it is elementary physics. Every student, after the first course of quantum mechanics, can understand it at the deepest level.
But if I
Why they didn't understand, do you want to say, or shall I say?
Just one thing, which is that what I never understood is why Wisner submitted his paper to a computer science journal rather than a physics journal. If he'd submitted to a physics journal, of course it would have been understood.
Well, even computer science specialists can understand it after 10 hours of quantum mechanics. But what was not understood, people didn't understand the basic concepts.
I think it was the wrong community, and I agree with Gilles that basically, if it had gone to a physics journal first. Now, I was Arthur Eckert's PhD supervisor, and one of my roles was to say to Arthur, put it into a physics journal, not a computer science journal, because they will understand the entanglement part of it and then propagate that through the rest of the community. So I think that it was really important to address the audience. What Stephen Wisner didn't do was to realize that he had a quantum solution and therefore start bringing the quantum community around on this one. And this is a bit of an issue for us in a multidisciplinary subject like quantum information, that one needs to bring these communities together to establish a common language. Now that's happened now, but going back to 1970, it didn't exist. So the common language took time.
So I was going to ask that. I mean, how much of the sort of delays and time lag involved in sort of creating these technologies is due to the fact that they are originating in what may be seen as quite an esoteric subject by a civil servant or somebody working in securities?
Yes, I would agree. I think there is still a gap between the physicists and the computer scientists in the field, yes. And the physicists have quite naive ideas about security and about loopholes and about everything. And the computer scientists have naive, hold on to ideas that they have got a quantum safe devised through lattice or whatever, but have not actually proven it, but know that RSA lasted 20 years, so the next sort of marvel will last the same sort of time. So I mean, there is and also can have this knowledge of how to make something truly secure, and what's actually needed out there on the street. That we physicists, we learn slowly about what actually is needed in a secure communication system and in something that works well and securely.
Is that true for you, Gilles? I mean, you said you were trained as a computer scientist, a cryptographer. Have you sort of had to learn how to do more and more practical, or see things from more and more of a practical point of view as you've had students engage with this and train students up to sort of go out and work in the real world on this?
Well, I was and I still am, first of all, a theoretician. I indeed had no background in physics when I met Charlie Bennett. And he taught me all I needed to know to start. I consider that my ignorance was a blessing. It's because I did not know physics that I was able to do things that any serious physicist would have known is impossible. Like teleportation.
But those things that we thought were impossible back in 1968 are now being realized in labs. I mean, people are storing qubits in arrays of atoms, of cold atoms and such like, as big as 2,000 atoms. You could sort of get a set of those pointy things that are on the banknote, stored in a lab, and using modern techniques of single photons through fibers to two labs, you can actually entangle two arrays in separate labs with full not CSH, but the full, what's the one? The Bell inequality that doesn't involve making any assumptions. Yes, you can get two.
Device independent.
What?
I mean device independent.
Device independent, yes.
Yes.
So this is now a practical reality. Have there been sort of obstacles put in the way in terms of government involvement, security service involvement that slowed progress?
Look, cryptography by definition is a cautious business. That's the first thing to say. Yes. And in particular, professional cryptographers will be worrying about the implementation. There's something that came out very clearly in Gilles' talk. So that what you saw was that when there are scientific approaches to a new way of doing cryptography, one has to bear in mind this is going to be implemented, and you look at the implementation flaws in it. So at that point, cautious cryptographers would say it's too early to start recommending the use of quantum key distribution in particular for sensitive government information. They would encourage further research in this. Now that's been the approach of the NSA, of GCHQ, and of the European information security people for quite a long time. Their position has morphed over the decades, where they're now saying that they would really like to encourage it. They encourage the idea of the hybrid side of it. But remember, you're not going to invest in a new approach to secure all of our e-commerce until you've kicked the tires. So I understand why they are cautious. It has been an inhibitor for companies to actually roll out these boxes commercially at scale. So they're still very much at the testbed level of things until we have enough information to overcome this fear that there's an implementation barrier.
If you allow me, I agree with what you say, with one exception, which is China, where they are taking it very seriously. They're using it for real, and they've deployed it on a massive scale that we could have done as well, but didn't. Right. Maybe we will at some point.
Yeah.
I'm glad you brought up China, because now I don't look like the paranoid one. How concerned should we be about? I mean, there's a lot of international sort of issues here in terms of collaboration between scientists, sort of slightly maybe in conflict with the idea that this is to do with national securities and corporate securities. I mean, how is that playing out?
At the academic level, everything is open. Everything I do, apart from maybe specific technologically useful or very valuable ideas, most of it is going to be published in the open literature, and I publish it as quickly as possible on the archive, within weeks, because I know somebody else is going to publish it. So within the academic community, there is this openness. But then there is, outside that academic community, there is the companies and the security services, and they have the opposite view. You saw that Clifford Cox invented RSA, or invented his version of it, years before the academics discovered it. So, and rightly so, because they are trying to protect secure information. We're trying to do science. We're not necessarily trying to create a military product. And as such, we're open and we collaborate, and we grow so much bigger by having that spirit of open collaboration. I mean, I saw it when I was in China a few weeks ago, that we were that this feeling is also being emphasized by the academics of China. It's not just us that says it. It's
Absolutely.
And so I would say but you have to then find a boundary,
right,
between those two views.
But at this very early stage of discovery science, we can see lots of examples where it becomes completely international. One of the things that Gilles contributed to was the idea of teleportation. Okay, teleportation came out of a collaboration between a large number of people, including from the UK, from Canada, from the US, and from Israel, and so on. Now, demonstrating that teleportation worked well, a group which involved Sandu and our Italian colleagues, a group that involved Jan Wei Pan and Zeilinger, all of these crossing multinational boundaries at this discovery phase. And I think that the acceleration of discovery would be really inhibited by these barriers that could be inserted. I did want to say one thing about Clifford Cox, by the way. You did mention that it wasn't used. It was, actually. It was used in secure telephony. Okay, a kind of Brent phone, if you know what a Brent phone is. So Clifford Cox stuff was actually used, but of course they never really rolled it out to realize the true potential internationally. Whereas the idea of the conceptual advances Gilles has represented, Sandu has represented, the experimental verification that John does, all of that has proceeded through a multinational quest for understanding, and I think that should and will continue.
Sandu, can I ask you?
May I just?
Yes, sorry.
There was Whitfield Diffie of Diffie and Hellman. Whitfield Diffie wrote a book in particular, in which he reports a conversation with Cliff Cox, in which Cliff would have told Diffie, "You guys have done a lot more with it than we did." Now, since he's from Secret Services, we don't know if it's true, but of Cox's own recognition, they could have done more. Let's put it this way.
Yeah.
So, Sandu, as somebody who works in sort of conceptual stuff and foundations, do you think there's any sort of conflict in terms of how you or how the field is interacting, because it's now a technology that is also dependent upon this?
Well, so as you say, I work on very conceptual things. Now, one of the interesting things in this new second revolution in quantum mechanics is how close the applications are to really fundamental physics. That is not the case in many other areas of physics. You need to develop from asking basic questions to go to very sophisticated things until the level you just start thinking of an application. And for many years, even thinking of fundamental aspects of physics was not very fashionable because the drive for applications. What has happened with the advent of quantum information is that suddenly, people could work on developing something, or at least having the theoretical idea of an immediate application to really very, very basic things. And Gilles mentioned Bell inequalities, Gilles mentioned entanglement, mentioned non-locality. This is not something that you would have expected in a talk by an engineer or somebody that does immediately applied things. So even if you think at the words quantum information, what they actually mean is that this was one of the great moments in science where two completely different things were put together. You had on one hand the theory of information, which dealt with abstract things, you know, letters of an alphabet, and you could send any message, or writing it by paper, or talking by telephone, or any other means, and suddenly a part of physics. And in fact, this started even before quantum mechanics with Charlie Bennett and Richard Feynman, who said every time when a computation process takes place or when a piece of information is sent or erased, we used some physical background, and we assume things about that physical background. That if I see a letter, I can copy it.
Yeah, and just for historical completeness, before Charles Bennett, there was Rolf Landauer. Yeah, Rolf Landauer was maybe the first person to realize the extent to which information is physical.
Yeah. So suddenly, these two things, that physics was on one side, and information was something abstract, computation was something abstract. You know, 1 + 1 = 2 has nothing to do with how you actually implement it. You write with chalk on a board or whatever. That is an abstract concept. And suddenly they came together. In quantum computers, it's not that we have a technology that moves faster. It does some sort of mathematics that doesn't exist when you want to implement it with classical objects, be there an abacus or the neurons in our brains. They can't do that. It is a different type of mathematics. So suddenly they come together. And things that were not fashionable, thinking of basic questions in physics. For example, one of the ingredients you use is the fact that you can choose at random a signal. Now, what do we mean by randomness? If I flip a coin and then I catch it, well, there are quite a lot of magicians that could know how to flip it well and would know exactly what it comes. You may, if you have a camera, you could follow the ball at the roulette and you can see, is there any true randomness? Well, quantum mechanics offers true randomness. Suddenly there are so many questions that are absolutely fundamental that suddenly come.
You mentioned quantum computers, and I'm sure everyone here is very interested to hear all your views on where things are at with hardware. And I know it's not your expertise, perhaps, and you may not want to offer opinions, but I'd be really interested, I'm sure we would, to sort of get a take on, there's newspaper articles come out, you can read in The Economist or the Financial Times, this is happening, this level of funding has been achieved by this group. I mean, do you feel that, we are on the verge of having a quantum computer that can operate Shor's algorithm in a way that is meaningful and impactful? And also, what are the other applications that don't get talked about enough?
Uh-oh, me.
I'm looking at you, Peter, yes.
If we look at the progress made over the past maybe 30 years in quantum computation, firstly, people have really been able to demonstrate very high fidelity, very high quality quantum bits and manipulate them. Then they're beginning to also look at ways in which you can get more of these bits. And we all knew that ever since Peter Shor and Andrew Steen, that you could in principle correct errors. But it's taken quite a long time to get to that threshold by which, if you tried to correct errors, you didn't make it worse. Okay? Now, that fault tolerance journey has taken a while, but it was really basically achieved in the last maybe 3 years. That we now have the potential to build machines where we can correct errors quantum mechanically. As soon as you can do that, you can see now you have a pathway. So for a very long time, we've done rough and ready estimates that it might be 15, 20 years away to a utility-scale quantum machine. I think the progress over the last 3 years has demonstrated that timescale has come down dramatically. My own feeling is that it's between 8 and 10 years now. And you can see that companies are pushing very hard towards a utility-scale machine. I think that there is every evidence that we have platforms that could begin to deliver. It's too early to down select on which platform,
I'm going to ask you anyway. I mean, is there a short list at least?
If you drew up a short list a while back, you would have said, yeah, it's going to be either photonic, ion traps, or superconductors, and you would not have included neutral atoms.
Yes.
Now, bingo, they're doing wonderful things with neutral atoms. So you have to be really careful to spot scientific progress. And when you down select, it has to be done on evidence, not by those who shout the loudest, who have got the largest amount of venture capital support, but those who've demonstrated the evidence that they're on a scalability journey.
And remember, people 100 years ago were still turning a handle to do their calculations on some sort of mechanical calculator that was replaced by valves in the 1930s, and valve computers were sort of built sort of in the war period, and then it was not really much individual transistors in 1950, 1950s and 60s, and it was only really in the 70s that the integrated chips began to take over, and silicon was settled on as the material. I mean, that silicon has had a long go and is a very good material now as a result. But there was a 50-year period in which the technology still was uncertain until it sort of settled on silicon. And I vote silicon eventually will
just because of the manufacturing infrastructure that exists.
A silicon-based platform, whether it's individual ions in silicon at low temperatures or it's a photonics version. They do shout loud. They don't shout loudly. They keep very quiet, but they have got a lot of venture capital.
I wanted to ask, I mean, is there a correlation between the amount of money you have, and I'm looking at IBM and Google, for instance, as well as some of the venture capital funded sort of implementations. Is there a correlation between that amount of money and the likelihood of success?
No.
Maybe.
Innovation and insight comes from unexpected places. Yes. What you've got to do is make sure you've encouraged that next generation who are going to surprise you. Because whatever we think now, 5 years' time, we'll think something else.
Okay.
So having money isn't enough. Having bright young people who tell us where you're wrong and there's another way is the way to do it.
Right. So are we in a position where we can at least say, we will get there with some of the existing technologies?
Yeah, look, right around the world, people are looking at the platforms, they're looking at their potentiality. In the UK, we have a benchmarking program that's looking at this. We purchased 7 or 8 test beds that we can kick the tires. That benchmarking will actually enable us to see what's around. Through the DARPA program in the US, they're doing much the same. Through the technology partnership between the UK and the US, we can now compare notes on this one. That will give us the evidence by which we can say, go this way. Evidence different from shouting.
Okay. Now that we've got a sort of limited time available until I open up the conversation to others, we can talk about non-locality. So I know you wanted to talk about it. We've only got 5 minutes. I mean, I like to, when I talk about these things, sometimes I talk about quantum cryptography as being based on something that we really don't understand, which is, these correlations and the Bell inequalities, and there's arguments about those things still, about what they mean, whether there is locality in nature. And I know you two have conflicting views on this. But what I wanted to sort of open up is that, and I'm going to come to you, Sandu, because I know you're kind of, non-partisan in this, in a sense. But these are all important discussions to still be having, aren't they?
Absolutely. Yes. So,
Gilles going to get his say anyway.
If I may not have my slides?
I don't know. You've only got 1 minute.
Oh, yeah, that's fine. That's fine. Is it off?
If it will work.
Your minute is gone.
Oh.
I'm sorry. I don't know if it come back on.
No. All right.
No, I don't know your password. If I did, I'd be very worried.
Can you not have my fingertip? All right. Yeah, in 1 minute, really. So the question here was, who told you that nature is non-local? And so these are the 2022 Nobel Prize winners. And their experiments seem to indicate non-locality. Clauser, who was the first person to prove experimentally these violations of Bell's inequality and think that he proved non-locality. In fact, he wanted to prove that quantum theory is wrong. He wanted to prove that Einstein is right and that the world is local and quantum theory is wrong. And he was betting on Einstein, and he was very sad that it went the other way. Now, was he very sad because he loved Einstein so much, or because it would have been a Nobel Prize next year instead of 50 years later? I don't know. But it's more interesting to, Alain Aspect says that it's clear Einstein's view that the world is local cannot be upheld. And he was an Einsteinian. He could not imagine how Einstein could be wrong, and he was sad. Clauser was very sad. Aspect was just sad. But he has to accept the result. And all these experiments were done to prove, they thought, non-locality. Because it seemed that if quantum theory is correct, then non-locality means that you do something here, and it has an instantaneous effect over there. So he really believes that you can have an interaction here that can, at a distance, instantaneously change the state of an object somewhere else. Alain Aspect wrote that explicitly in his book. Very nice book, by the way. See Einstein, ABC had Einstein known. So he believes in spooky action at a distance. Zeilinger is more nuanced. He says all experiments, all that they can tell us is that nature cannot be described locally in the sense of Bell. That's correct, in the sense of Bell. But to say that nature is non-local is going too far, and he's right.
I'm going to cut you off there if I can.
No, you can't.
I knew I couldn't do it twice in one night.
No, I'm really almost done about this, which is that Zeilinger says you should read this book in which Einstein wrote his autobiography. And there you see what Einstein meant by locality. There's one supposition, one being in italics, that we should absolutely keep in Einstein's mind, which is that the real spectral situation of the state of a system here is independent of what happens there. And the whole point of this added minute that I was given, the whole point is that this has nothing to do with what the experiments claim to have proven about non-locality. What they've done is to prove that there's no local invariables, but this is absolutely irrelevant to proving non-locality, because there are other ways to be local. That in Einstein's sense, there's other ways to be local than to be local in the sense of Bell with local invariables. And this was demonstrated at the turn of the century, 25 years ago, by Deutsch and Hayden. So there's nothing new here. We've known for 25 years that quantum theory is completely compatible with a local view of the world.
Thank you. Okay. I'm not cutting you off. I'll let you finish. Sandu, okay. What's your take on that?
Well,
in 1 minute.
Oh, it's very simple. Gilles is absolutely right, but he's hiding some of the things. And he doesn't tell you the relevant thing, because from his point of view, there doesn't exist only this world. There exist many other worlds which you never see, you will never experience, and there is not a single result that you've ever seen in the lab, because the moment you see it, it's not you, there are many copies of you. And there are many copies here of Alice, and there are many copies of Bob, and when Alice and Bob come, it's not only one, but all these copies, and how they join together depends on the results, which are not only one result, but many results. And it goes outside of science. It's good to envisage it, because it allows you to ask the questions in a sharper way. But actually, all these things go down a long way. Goes down to Einstein, who thought that God doesn't play dice, because quantum mechanics is supposed to be a non-deterministic theory of nature. We are used with the fact that we repeat the same experiment in exactly the same condition, we'll get the same results. The same causes produce the same effects. Of course, there could be some experimental errors, but they can be made smaller and smaller and smaller, and then the results are more and more reproducible. Quantum mechanics, as far as we see it, not in all the other worlds that we may not experience, it is completely random. And things came from this. Einstein wrote then one of these famous papers, the Einstein-Podolsky-Rosen, but talking where he thought that he was able to prove that quantum mechanics that predicts this is incorrect. Now, rather than entering to this, what I want to tell you that although quantum mechanics has been with us for at least 100 years, if not more, if we start from 1900, and although we know the equations of quantum mechanics, and we can predict within our computational capacity the results of all experiments, what they will show, it is very, very counterintuitive. And it is a general assumption among physicists that we don't really understand what is going on.
I'm going to stop you there because I think that's a perfect ending, which is why we all actually very much enjoy quantum conversations. I'm going to ask you for your questions in a moment, but we do have one audience question that's come in from a man whose face is fortuitously up on the screen right now. So we have a question from David Deutsch for Gilles. I know you're very good friends. But the question is, do you think that mathematical milestones for quantum computation, such as quantum supremacy, are of any value philosophically or for theoretical physics? And either way, what would you regard as a reasonable criterion for having achieved full quantum universality in the laboratory? And I guess this is going to come to all of you in some. I mean, are the milestones important?
Well, I think that is very important. We can do physics purely from a theoretical point of view, like Einstein did, but Einstein would not have developed his theories if experimentalists had not come before him to arrive at strange effects that Einstein was able to explain. And at the moment, we believe that we understand, I'm sorry to disagree with you, that we understand quantum theory. And would experiment help us understand it better? Possibly. I know that David Deutsch believes that a fully working quantum computer could only be explained if we believe in many world interpretation, because it's able to do an exponential number of computation at the same time, where exponential could mean more computations simultaneously in a quantum computer than the number of particles in the universe. And once we achieve that for real, not only as a theory, but experimentally, once we're able to do that, then for David Deutsch is a proof that these, at least a very strong argument, I believe that he says that these computations can only be done in exponentially many parallel universes. And for him, when the quantum computer will be a reality, that will be the proof of all these parallel universes.
Peter, I can see you shaking your head there. I'm just going to...
I've never been a fan of many worlds. I think it's profligate on universes.
Well, maybe you are. That's right. In other universes, you might be a fan of them.
I know. But David's other point, though, is looking at ways in which you get a quantum machine that has an advantage over classical machines. That's a separate question.
That's an important question.
And of course, I think we all agreed in the community not to use the word quantum supremacy anymore, by the way.
Yes.
Quantum advantage.
Yes.
And what you'll see is an arms race between those people who design really clever algorithms classically and the quantum machine. When the very beginnings of the Google machine results came out, it looked like you couldn't do these even on the largest supercomputer in a reasonable time. Then they found ways of actually changing that. So you're seeing an arms race between the two. And every now and again, people will think of a method that looks like it's going to give you a tremendous advantage. Then very clever algorithmic people can find a way of doing it with a classical machine. Nevertheless, if you could get 300 quantum bits under complete control and the ability to manipulate them, you have a state space that's 2 to the 300. That is larger than the number of particles in the visible universe. Okay? So there will be a breakpoint at some point on this one. At the moment, we're still with toy models. And toy models, you will always find this arms race competition of finding ways in which you can accelerate high-performance computing compared with the quantum machine. But eventually, just because of this exponential scaling, things will take off on the quantum machine.
John, quickly. And then we'll move on.
A more pragmatic view is it probably answers the question as to why these results are appearing in the literature. We're all mostly academics here. We know that if we don't publish our results, we don't get any funding from EPSERC or our funding agencies because we can't prove that we're doing good science. So these are guys that are operating on maybe a couple of orders of magnitude larger scale in terms of their next grant. It's not a next grant, it's a venture capital or an investment from a large company. And so they're like us, they're having to publish the results. Even the ones that have been hiding for a few years have published recently. Our friends in PsiQuantum have published a paper on the photonic quantum computing. It brings the money, and you have to be visible to bring investors into this. And we're not going to build a quantum computer for 50 million. It is going to take $500 million or more.
Yeah. Okay. Do we have questions in the audience? I believe there are microphones. Let me see what hands are going to go up. There's a gentleman here at the front. I think was the first one.
This is drifted into one.
Here, sorry.
A couple of weeks.
If you can keep your hands up, then I can kind of get an idea of.
Thank you very much to Gilles and all the panelists for your wonderfully interesting area. I started off in physics in 1976, and I moved to psychology. And I want to go on from what Sandu said. He talked about neurons and classical ways of thinking about this. I wonder if the brain is quantum entangled. I know warm and wet doesn't allow it, but is it quantum entangled?
Well,
for a femtosecond.
As far as I can see, it is not. So, on the other hand, we discussed today about quantum biology, which is a completely different thing. These quantum effects, all the ones that we talk here, are very, very sensitive. Any amount of noise, definitely the amount of noise in biological systems, which are hot and wet and so on, they destroy the quantum effects. The ones of the second revolution, where you want to interact different particles and depending on their correlation to do something. There are obviously quantum effects at the basic things. The atoms are quantum, the molecules are quantum. But there exists an intermediate regime in which you have bigger molecules, that, like molecule of chlorophyll, that nobody would have imagined at that scale to have quantum effects, and it turns out that there are. Yeah. So there exists an intermediate and very interesting part of biology. That doesn't go into entangled brains. That is, it's still a molecule, not a whole brain. But especially photosynthesis, that is one of the processes most common in nature, that got very, very optimized. So that it is not clear whether they are useful or they are just secondary for what happens there, but there are quantum effects there.
I'm going to move straight. There's a gentleman here in the middle who's kept his hand up the whole time. I did mean only for a moment, just so I could sort of gauge things. So thank you.
Thank you. I'm interested in the quantum hacking of QKD. What imperfections have been exploited, and what should us theorists be careful of assuming about implementations in the real world with future cryptographic systems?
Go on, John.
Well, you can manipulate most experiments use inefficient detectors that are not 100% efficient, apart from these these device-independent protocols. But most of the protocols out there use detectors which can be manipulated. You can manipulate their efficiency, or even make them blind at particular moments in time. And there are protocols like that that sort of sends bright light in at the right time. We've tried to do it in the lab, and it is very difficult to do because particularly if you want to sort of measure, if you use that bright light to measure, say, the state of your polarizers in a polarization-based QKD, or your phase shifters in a phase-dependent QKD. That's very difficult, but you can, yes, but again, there are protocols that Vadim and other co-workers have thought up. So they're difficult, but it has been proven that you can do some things with on the detectors.
But sorry, I'd like to piggyback on this because there's a good news here, which is that among the protocols that have been implemented in real life, there are those known as measurement device independent. And we know how to get a secure key even if the detectors are in the hands of the eavesdropper completely. That's the easy part to getting what we call device independence. So we know exactly how to fight the threat of detectors being hacked. It's the sources that's harder. And not only that, but at some point the world record distance for the establishment of a key was with one of those protocols. So it's not. This is not just theory. In practice, we can use these measurement device independent protocols, and completely foolproof against manipulations by bad people of the detectors. And the detectors can be put in the hands of the eavesdropper, and it's still secure.
There's a gentleman in a pink T-shirt.
Hi. We've heard a bit about what's happening in the UK, in Europe, in China. Just to be a bit more explicit, how would you compare the academic and technological progress in those places, and also America and Japan and anywhere else?
Want a global survey?
Yeah, there are such surveys around. In particular, you can look at the intellectual vitality through the impact of publications, and there are statistics on this. You can look at the impact in terms of venture capital raised and so on. So there are measures on this one. The most recent one that I've seen, that I believe is by MIT, and if you know me at the end, I'll give you the link to it. There are others, of course, that look at these things, usually management consultancies, and then I think a pinch of salt would be perfectly respectable approach. But there are measures in terms of the impact of the science. China has by far the largest program, followed by the US, followed by the UK into this. But that is a blanket statement. What about the niche activities where there are particular strengths in particular places, where right around the world there are world-leading things going on in different places? So don't just do an average over a nation.
Okay, there's a gentleman here in the light blue blazer.
So I have a question about QKD. Most of the demonstration of QKD, at least as far as I know, establish a key and then use AES to do high bandwidth communication. So do you envision in the future that we can do only pure QKD? Because if we do AES, we're back to square one, in a sense. And people kind of hide this under the rug sometimes when they talk about demonstrations of QKD.
Well, I would give a double answer. One is that there have been cases where the key established with quantum cryptography is used with as a one-time pad and is absolutely secure, as long as the transmission was not hacked while in progress. But my other answer is, and at some point I didn't like the idea of people using AES after quantum keys establishment, because I thought, what's the point of doing something that's absolutely secure and then spoil it with a system that is not proven secure, that's not competition, that's not information statistics secure. But then I changed my mind, because AES, as opposed to RSA or Diffie-Hellman, there's no reason really to believe that AES is weakened by quantum computing, except by Grover's algorithm, so that if you have a key twice as long, you're as secure against a quantum attack as the key half as long would have been classically. So I'm not saying AES is secure, it's quantum secure, I'm not saying that, but I'm saying that the quantum advantage that you would get as an eavesdropper against AES is probably not significant as opposed to against a key establishment scheme. So once you establish the key with quantum cryptography, if you use it with a classical system, it's probably not so bad. But it's better if you can use a one-time pad.
And of course, you can continually create new key with quantum cryptography. Yes. So you can rekey your AES system many orders of magnitude more frequently with a generated key.
Yeah, and that's very important, actually, because the main tool that cryptanalysts use against for their cryptanalysis is redundancy, and the longer is the ciphertext, the easier it is against a classical system, secret key system. The longer is the ciphertext, the easier it is to find the key. So by rekeying, using quantum key establishment, by rekeying your AES every second, you deprive the eavesdropper from two things. One is very long ciphertext on which it's easier to do cryptanalysis. And the other is that if they manage to break one block, then a second later, they're back to the starting square, and you have to do it again. So that's one of the big advantages of quantum computer establishment, rekey AES every second.
I'm going to give the last question to the man in the hoodie at the back there. Thank you.
Thank you. There's been some mention of lattice-based quantum cryptography today, and there was an attempt by Oded Regev, I think last year, 2 years ago, to for a proposal for a quantum algorithm to break this form of cryptography, which fortunately or unfortunately had a mistake. Right. And I'm just curious if you think we'll be able to break lattice-based cryptography with quantum computing or not, and why?
Who knows?
Well, that's the whole point. We have no way to prove otherwise. Exactly. Until someone finds how to break it. Before Peter Shor came along, there was no reason to believe that factoring would be easy on a quantum computer. So it really, who knows is the right answer.
Okay.
Yeah. So the challenge for the lattice-based sort of cryptography is prove without a doubt that your system is secure, even against the quantum. Prove it.
And on that bombshell. Thank you so much for your questions. Thank you to the panel. Could you please join me in just thanking them for their expertise? And I'm going to hand back to Martin.
Thank you, Michael. Thank you for this. Tonight was truly a celebration, I think. Mission accomplished from Professor Brassard for that fascinating discussion. Of course, I'd like to thank Professor Brassard on accepting our invitation at the Quebec Annual Lecture this year. There's going to be a few thank you. Merci à l'Université de Montréal. Merci au recteur Jutras, Valérie, Frédéric, Isabelle, Michael, les deux Sophie. There's two Sophie at the University of Montreal who were really helpful also. Thank you for everyone on that. Our esteemed panelists, Sir Peter Knight, Sandu Popescu, Professor John Rarity, and of course, of wonderful moderator. Michael Brooks, thank you for that. Thank you for the Royal Society for this wonderful, incredible, historical ground that we are really honored to be in tonight. And the last thank you is for all of you being here tonight to hear that discussion, and to our team at the Quebec Government Office in London, Rémi, Kaya, Raphael, Barbara, and a lot of more people. I don't want to name everyone, but just thank you for everyone on that. So we're going to switch now to the reception so you can continue to interact with our panelists, with Professor Brassard. So we're going to have a reception opening right now for drinks and if you can, à paye. So thank you, everyone. Merci beaucoup et bonne soirée.